Okay, so yesterday we finished up chapter 4, and that was on log functions. The last two functions we're going to study in the algebra part of this class are in chapter 5, and they're exponentials, which we'll spend one section on, and then the section after that, log functions, logarithms. And we'll spend two sections on that one. So let's just compare these two expressions, x to the second power and 2 to the x. Okay, they're different, right? If you look at where the variable is, one of those is exponential, one of them isn't. Okay. They each have a base and an exponent. So if I scroll down a little bit, so the base is always the number that's lower, the exponent's always the number that's, well, I can't say number, it's the thing that's higher. And when you write something like on the left, a variable for the base, and a fixed number for the exponent. Okay. Something like I have here, this is a polynomial. Okay. That's a quadratic polynomial. It's x to the second power. What I have on the right, that's exponential. Okay. The reason it's exponential partly is because there's a variable in the exponent. Okay. And the other thing that makes it exponential has to do with the base. The base can't be anything. It can be a lot of things, but there's a restriction on what the base can be. So we'll talk about that. So any question on the difference between the two expressions? I'm kind of focusing on where the letter is. All right. So we're going to be looking at things that are on the right. Okay, things that look like that. So when you put the variable in the base, that's like the one on the left, and the exponent is a non-negative integer. Bless you. Non-negative integer, that means it's not a fraction, not a decimal. Okay, as long as it's a non-negative integer, that makes it a polynomial. Could be a quadratic, could be a cubic, x cubed, could be quartic, if that's a fourth power. But the point is, anything with that fits this description is a polynomial. Okay. We studied polynomials back in chapter I think it was 2 or 3. Okay. And we did all kinds of things with them. We found like where they're increasing, decreasing, local min, local max. That's when we did all that stuff. So now, this is what happens. This is the case where you have an exponential. If your variable is an exponent, and the base is a positive real number, except 1. Because think about what would happen if the base was 1. 1 to any power is always what number? 1. It's always 1. Even if you do 1 to the 100th power. It's just 1 times 1 100 times. It's still 1. Exponential functions curve very sharply. They can either curve up, that's called exponential growth, or they can curve down, that's exponential decay. But if you take 1 to a huge power or 1 to a small number, it's always 1. So that's not exponential. That's called a constant function. It just stays the same. Okay. So as long as your base is a positive real number, that's not 1, and your variable is in the exponent, you have an exponential function. And exponential functions are one of the fastest growing ones we have. They curve up very, very sharp. Question on the definition for an exponential function? It's pretty straightforward. It's nothing super tricky. So let's look at an example of one. Let's graph 2 to the x. I picked a base that's positive. It can be a fraction, that's okay. The base can be any positive number. Like 1.3, that works. But the variable has to be an exponent. Okay, so it kind of stays flat for a while, and then all of a sudden, when it crosses the y-axis, it starts curving up very sharp. So if you look at the domain is left to right. This graph is going to go left forever. That's why it's negative infinity. And it is going to go right forever. If you're saying, well, isn't it going up? Yeah, it's going up, but it's still going to the right slowly. All right? It goes up a lot faster than it goes to the right, but it does keep going to the right. Now, does it look like the graph goes up forever? What do you think, based on what you can see there? Yeah, it does. It goes up forever. Does it look like it goes down forever?
Yeah.
You say yes, Jake?
Maybe, yeah.
You're not sure? Well, pretend like what we see there is what it's going to keep doing. It's not going to like do any weird turns off the screen. It's pretty much just going to look like that. No, it's almost like it comes down and it levels off. Okay, and in this case, it's leveling off at 0. Okay, so I didn't actually. Let me write that in. So the range is from 0 to infinity. It never reaches 0. It just comes down and it gets very, very, very close. Okay, we already said this on the other page, that a is a positive real number not equal to 1. So I already said that. Okay, so range is 0 up to infinity. If you're not sure if it reaches 0, just go on your table and plug in some negative numbers and see what happens. You get 9.8 times 10 to the negative 4th power. That's just 0.000009. It's a very, very small number. All right? But it will never reach 0. Okay, those are all examples of exponential functions. Okay, if you want to write down some other examples. 10 to the x, 4 to the v, even pi to the x. The base there are all positive numbers. None of the bases are 1. And they all have variables in the exponent. Those are examples of things that are not exponential functions. The first one is a polynomial. It's a cubic. Okay. The f of x under the non-exponential, it has a number for an exponent. No, you can't have numbers as exponents with what we're talking about today. Same thing here in g of x, there's a number as the exponent. And then the last one, y equals, well, it's kind of like a rational function because it's a fraction, but then there's a radical on the top. So it's kind of a combination of a radical, which we studied yesterday, and a rational. That's not exponential at all. Okay. So let's look at the difference between 2 to the x and 3 to the x. If we graph them, they're both exponential, but one of them is going to curve up faster than the other. Anyone have a guess which one curves up faster? Shot?
3.
3 to the x, yeah. So let's graph 3 to the x. And see what it looks like. So it's kind of hard to tell at first because they're so flat in this section, you can't even really tell. But look what happens after they cross the y-axis. The red one starts curving up sooner. It curves up faster. And that's because if you take 3 and raise it to a power, and 2 and raise it to the same power, well, generally 3 to the power is bigger. Okay, when your power starts getting bigger and bigger. So that's all I wanted you to see. If I were to graph 5 to the x, it would curve up even sharper than those other ones. Okay. So eventually it's going to look like it almost takes a right angle. It'll curve up extremely sharp. There'll still be a little curve, but it starts to get less and less. Questions on the difference between 2 to the x and 3 to the x? Okay. So sometime what's going to happen is we're going to have negative exponents. That can be a little confusing. So what we want to do is if we have something with a negative exponent, we're going to try to write it so that it doesn't have a negative exponent. So when you have something like to the negative 1 power, that just means to flip it. Right? Okay. In general, what a negative means, like if I had let's say like 3 to the negative 2 power, the negative tells you on an exponent that it should go in the bottom of a fraction. So that means that. Okay, so a negative exponent just means if you want to make it positive, take the whole thing and put it in the bottom of a fraction. All right. So this is just like a to the first power, even though I didn't write it that way. All right. So let's see what happens if we had something that looks like an exponential function. We'll pretend a is some number that's positive, but not 1. And it had a negative exponent. Well, what number is in front of that x, even though it's not written? Yeah, it's like having a negative and then a 1 right in front of the x. So that's multiplication. Negative 1 times x. Well, if you think back to when would you multiply two numbers in an exponent? Well, if you had something like 2 cubed to the 4th, the way you would do that out is like this. Whenever you have a power to a power, you multiply the two powers together, and that's your new exponent. So that's like 2 to the 12th. Well, let's look at this one. We're multiplying two numbers together, so that must have been a power to a power. One of the powers is negative 1, the other power is x. So if you multiply negative 1 times x, you get exactly what we started with. So power to a power, multiply exponents. And now, I'm going to take that and substitute it in right there, because we just talked about what a to the negative 1 is. So what ends up happening, okay, if you kind of want to take a shortcut, is if you have something with a negative exponent, all you have to do is flip what's inside, and it makes the exponent positive. Okay. So if you gave me something like, let's do 4 to the negative x power, and I wanted to figure that out and look at it, but only have positive exponents, just take what's inside, whatever a is, and flip it. Make it 1 over a. And once you do that, you can make your exponent from a negative to a positive. So 4 to the negative x is exactly the same as 1/4 to the x. Just flip the base. Right? And that's helpful because when we look at the base, there's certain times where you're going to have graphs that go like this, that curve up. I already showed you a couple like that. You're also going to have ones that curve down. Whether it curves up or down is all controlled by that number. This one would curve down if you drew it. Okay? It all depends, is your base bigger than 1 or is it less than 1? Okay. And somebody looking at this one on the left may say, oh, the base is bigger than 1, it's 4. Yeah, but the exponent is negative, so that changes it. So we always want to look at it with a positive exponent, and that's how you do it. Any questions on that? So let's graph these and take a look. Now this one you could rewrite if you wanted. What do I do with the 2 in g of x if I wanted to make the exponent positive? Yeah.
It would be like 1 over 2 to the x would be a 7.
Yeah. So when I graph these, you can type g of x in either way. It doesn't really matter. But that's how you could rewrite it if you wanted a positive exponent. So let's look at turning the calculator on. And we've got 2 to the x. And I'm going to type it in as 1/2 to the x. Yeah, it's a few more buttons, especially if you press the right ones. But it's okay. 1/2 to the x. Okay, let's hit graph and just see what it looks like. So there's 2 to the x. That's starting off very slow. and then curves up. Now look at 1/2 to the x. It curves down. Curves down. It curves down, and it flattens out. It's basically a mirror image. Okay? If you flip the blue line, or the blue curve and the red curve on the y-axis, they're mirror images. Okay, so let's just kind of describe what's happening here. So let's look at the domain and range of the one in blue and then the one in red. All right, so the first one is f of x. That's the graph in blue. We actually already did this one, but what was the domain for the graph in blue? How far left and right does that one go? Yeah, infinity. So it's negative infinity to infinity. Well, if you look at the graph in red, it's the same thing. If something goes left and right forever, and you just mirror image it, it still goes left and right forever. So the graph in red, it goes up as you go to the left, but it's also going left. But it's definitely going up more than left. Okay, it goes up very fast as you head left. So that one's also negative infinity to infinity. Now, the range doesn't go down forever. What's the lowest value that, we'll start with the graph in blue, that it goes to, but it never hits? Yeah, 0. And that's the same for the graph in red. The graph in red comes down and it gets close to 0, but it never reaches it. Okay? So they actually have the same, same domain and the same range. Okay, when you make an interval, you always start low to high. I know that the graph looks different, but that's how you write an interval. Low to high. Don't say the range is infinity to 0. It's kind of weird. Okay, 0 to infinity. Okay, any questions on that? Okay. So let's try to summarize what's happening here, okay, in general. So I did the problem specifically when a was a 2. Well, let's just pretend that a is any number, any positive real number. 2, 3, 4, 5.5, 6, whatever you want. This is how the graphs are pretty much always going to look, right? If you graph 2 to the x, 3 to the x, 10 to the x, 12 to the x, they're all going to curve up to the right. Now, if you take all those numbers I just said and flip them, 1/2 to the x, 1/3 to the x, 1/5 to the x, they're all going to look like the graph in red. Different amounts of curve, but they're all going to curve down and to the right. So, in general, if you're looking at a graph like f of x, okay, you have a, where it's a number that's not a fraction, okay, a number bigger than 1. As you head to the right, your y value heads up. So as x gets bigger and bigger, y gets bigger and bigger. As x gets smaller and smaller, okay, so as you head, or more and more negative, okay, as x heads to the left, the y value is approaching 0 but never reaching it. Okay, and that's for any graph that's a number bigger than 1 to the x, 2 to the x, 10 to the x, anything like that. Now, let's look at the graph in red. That one's different. As x heads to the right, what happens with the graph in red? What does the y value get closer and closer to? 0. Yeah. So as x heads towards infinity, it's to the right, the y value on the red graph is coming down. It's getting closer and closer to 0. How about as x heads towards negative infinity on the red graph? It heads towards infinity. Okay. So f of x is like your blue graph, and g of x is like the red graph we just did. G of x is the fraction. Okay. We did the fraction 1 over 2, but it could have been 1 over 3, 1 over 4. Could have been anything. Okay, we're back. So yeah, there's the behavior of those kinds of graphs. So it's all controlled by the base. Okay. The key difference is your base greater than 1? If you have a base greater than 1, your graph looks like that. If you have a base between 0 and 1, like 1/2, 1/3, anything like that, your graph looks like that. So it either curves up to the right or down to the right. Any question on that? Okay, but just remember, if you've got something like this, that's kind of hiding the fact that the base is 1/4. Okay, you want to always make sure you have positive exponents if you're following this rule. Okay, so always make your exponents positive first. Okay, so we can transform exponential functions exactly the same way we've transformed every other function all year. There's nothing different at all. So let's just write out the different letters and what would happen. All right, so let's say I had a to the x. That's my basic function. If I put a plus inside, that would do something. If I multiply inside, that would do something. If I multiply outside, that would do something. And if I add or subtract outside, that would do something else. The stuff inside is always your what? Horizontal or vertical? It's always the horizontal. Adding is always a shift. Multiplying is always a stretch. Now I'm outside. So when I multiply outside, D is a vertical stretch. E is outside, and when I say outside, I mean outside this. What I just circled, that's the exponential. Okay? C and B are inside the exponent of the exponential, so those are inside. D and E are outside. Vertical shift. It's exactly what we did yesterday. If you make C negative, that would cause a flip. If you make D negative, that would cause a flip. Which way? Well, if C is negative, it's a horizontal flip. If D is negative, it's a vertical flip. And remember, C and D do the opposite of what you would expect. Right? So if you see plus on a horizontal shift would actually move it left. Minus on a horizontal shift would move it right. Okay. So we'll finish up with the transformations on this one. And that'll probably be a good place to stop. Okay, so we're comparing g of x to f of x. You don't have to tell me what yet, but just how many things do you have to do to change f of x to g of x? How many transformations? Yeah?
Oh, I didn't see the negative side.
So what do you think now? How many? You not sure? Anyone have a thought how many we got to do? Mike?
3.
3. There's a shift, a stretch, and another shift. Now, I tried to use letters that went with the order you look at each arrow. So do B, do C, do D, and then do E. if you have them all. If you don't, skip it. So we'll start with the plus 1. What would the plus 1 do? It would shift left, yes. So shift left 1. Second transformation, all right? I don't have a number in front of x, so I can ignore c. There is no horizontal stretch in this problem. The 2. What would the 2 cause to happen? Yeah.
A vertical stretch.
Yep, by how much? 2. Yep, vertical stretch by factor of 2. Right. And the last part would be the minus 5, which would do what? Yeah.
Vertical shift.
How much?
5. Or is this against where outside like not?
Vertical, it does exactly what you would expect.
Okay, so it's not 5.
Down 5. Shift down 5. So we got a good part of it done. I'm going to give you the homework, but again, if you get stuck, don't worry because it's probably half the questions we haven't gone over yet. But I'll give it to you so you have it, and then we'll finish up the lesson next time we have class. We were almost done. We had probably about 15 more minutes. Okay. So homework tonight is on page 268. It's 4 through 7, 19, 25, 27, 31, 35, 47 to 49, and 57. Again, there's like 6 or 7, actually it's probably like 7 or 8 questions there that we haven't done yet. We haven't done half-life, and we haven't done like double. So if you get stuck, don't be like, what's going on? We're going to finish the lesson tomorrow. So just do what you can, and that's good.